CLI a cross-platform IDE for C and C++. Download now.
Hello, my name is Dietmar Kühl. I work at Bloomberg. I work mostly on market data distribution, and my main interest is not so much necessarily multiple processing, but rather kind of concurrent working or asynchronous working in networking. This is where that came from. The actual work on the sender-receiver stuff and what I'm presenting over here is mostly my spare time exercise rather than my real-time work, but it's inspired by my actual real work. So, personally, I'm very excited about cplusplus 26. Lots of people are excited about different things. They should all be excited about stood execution. All the other nonsense which is there, contracts, reflection, yeah, it doesn't matter. Right? This stuff matters. And basically what that adds is an abstraction for asynchronous operations going under the name sender-receiver, which is a really awkward name. I'm not a fan, but this is how it's called and everybody uses it. It's basically a framework for asynchronous work and composing algorithms. And the implementation comes, as Lucian just showed, with a bunch of fundamental algorithms, things like van all, open error, which just rewrites the result and things, and hopefully some tools like counting scope. Lucian kind of put me a little bit on the spot in the previous presentation saying, all right, what about task? There's a proposal for task, but it came late because nobody wrote it. So let's see where that goes. I hope for cplusplus 26, but not yet convinced. So, but I've presented in that space a bunch of times before, often doing live coding in the last couple of years, but I realized when people pointed out that what I'm presenting is I did it the wrong way around. I showed how to implement the basics, then I showed how to implement the tasks, then I showed how to actually use it without actually saying, why are we doing all that nonsense at all? So I want to rectify that and basically provide the first talk in a series after giving the other three, basically talking about why asynchronous, why is that important at all, and what are the key ideas in the space. So when people ask, oh, why do asynchronous at all? Let's turn it around. Why synchronous anyway? Like a lot of the programming we do is actually often you end up accessing a file, you access a database. All of these things are asynchronous. Right? Whenever you have anything inside your code which may block, this is where asynchronicity comes in. Sure, we do have some parts of our programs which are just computations, but maybe a show of hands, whose computations mostly do actually, or programs mostly do computations rather than accessing I/O, a database or anything like that? Really? Half the people do mostly computations? That's interesting. Scientists, all right, oh these, all right, fine. Sure. Okay, so some people do that, but even then, I think their software is actually not running off. Well, it needs to get data from somewhere. That would be asynchronous. And often it's embedded into a service or something like that. There's asynchronicity in there. So in my mind, most of the program isn't really synchronous. Most of it's actually asynchronous, should be asynchronous. So, and with the idea being the processor is always busy. It never, or a thread is never, is always busy. It never waits for something to happen. And this is the basic idea of the whole thing. So like anything, when you have interactions, like we often, if you create a UI programming thing, I know a few people do that, but anybody using Qt, as we have seen in the keynote, for example, this should be asynchronous, and it's all guided towards asynchronous. Anything waiting for a keyboard, right? The thread should not wait for anybody pushing keyboard or pushing a mouse or a trackpad or whatever it is, some pointing device around or pressing a button. And the way, if you want to have any of that in your program, you have basically two options how you can do that. Either you do it asynchronously, which means you request something, but once you have requested it, you only wait for the completion that it arrives. and you act then. And the other alternative is you have multiple threads, but often having multiple threads just so that you can deal with a little bit of user interaction while you display whatever you display, or it doesn't make much sense. And in a very similar sense, a lot of servers, this is more the area where I work, is basically a server can process synchronously one client, right? It gets a request, processes the client, and carries on. If you want to do many clients at the same time, because often servers actually just ask other servers for other work, or look at a database, which is just a server, or look at a file, which is actually another server. It's just a file server typically. It's not necessarily local memory. So this is all asynchronous stuff. So while we are waiting for that I/O to happen, we would possibly like to process other things. Again, the way you can do it is, yes, you can spawn more threads. Maybe you spawn more processes, but whether you have threads or processes, same thing. And these things often add complexity, which you don't really need or want. And and threads themselves, actually, if you actually do have lots of compute, anybody who has lots of compute, I would imagine that they actually spawn multiple threads or use a GPU. Again, this is an asynchronous interface. You basically kick work off, and you want eventually to reap the results. So it's the same thing as just within the computer, basically talking to another service within the computer. Like the CPU itself is actually also asynchronous. If you look at it, it's kind of when the CPU wants memory, it basically sends a request on a memory bus to have data come back. And interestingly, Gornishov actually showed a use case for his coroutines to actually asynchronously request, give me this memory and give me this other memory, to then basically channel that. And once memory was there, then actually use it. So even on that level, it may be things may be asynchronous. But if you do deal with threads, you basically still need to do some kind of synchronization, and pretty much a solution just presented saying, right, we don't really want to think about that. We want to think about the workflow. And this can be entirely modeled as asynchronous workflows, where you ask for something, and whatever the system does to execute that concurrently, possibly, you don't really care about that. You basically just carry on working once a result happens. So that's in my mind, just the same thing. It's kind of whether you do I/O or you talk to other threads. All of these things are asynchronous. And another important reason why asynchronously is something really, really crucial is often libraries who want to do things, who need to do, well, maybe they have whatever requests going on, maybe they talk anywhere. They need to have a way to actually execute that. And often these libraries either require that you give them a bunch of threads, or worse, they actually create the threads internally themselves. Like at Bloomberg, we have, for example, a message passing interface. And if anybody uses that, that process will spin up a whole bunch of dozens of threads which are just for this message passing thing. As an application, I cannot use that. They may be just sitting there waiting for inputs to come, but this seems to be not a good idea. So any library which have basically do I/Os probably should rather have an asynchronous interface to things as well, so that basically the processing comes from let's say a thread pool or something, while the libraries are actually kind of sort of thread agnostic. They go, right, you call me and you give me the resources, and I come and somewhere it is running. It may be a thread pool, but if I don't really have a lot of interaction, I don't need to create a pool. I may have just one thread. And especially the one thread case where you do multiple things at the same time, waiting for things, is a really attractive one. While you may want to structure everything as kind of your workflows, and you don't really want to pay attention to any of the synchronization, existing software probably requires some level of synchronization unless you have just one thread. in which case you get entirely rid of that. So I think there's a benefit in there as well. So all of these things are all just asynchronous, and this is nothing new for that matter either. The in something like a UI interface like Qt obviously does asynchronous stuff. Databases often have an asynchronous interface. Not all have, but often they have an asynchronous interface. Files is a little bit different. Most of the time, files do not have an asynchronous interface for whatever strange reason. Although the operating system interfaces do get there. For example, libiuring was entirely created to have asynchronous file I/O. So if we can actually utilize that, we can make file I/O entirely asynchronous and get data once it is there. So all of these things want to be asynchronous. So nothing is new in the sense of a lot of these things are done in the past. The thing which is changing in my mind is instead of everybody doing their own thing in a more or less composable way, there's a standard interface that actually is composable. And the composition is something which is, in my mind, really key, which you can already see by saying, right, we define a number of standard components, and there are already add-on things like the counting scope or the task, which basically build on that interface. And you can build other tools to go, right, everybody who plugs into this standard interface gets the same benefit. Okay, just for another reason why you may want to use asynchronously instead of threads. In practice, it turns out you can create actually more open files than you can create threads. It doesn't seem to be that there's an inherent limitation that threads get massively slow or something like that, but there seems to be a limit on how many threads can I create on a given system before the system goes kind of, oh no, thread creation just fails. You can typically create, or at least set with some parameters to say, all right, I can create that many files. If you want to have something like a server having lots of connections, over there you may not be able to just have a blocking read on every connection, but it's quite easy to basically have asynchronous work sitting on file descriptors while using a much, much smaller number of threads. And in principle, it seems like a good idea of how many threads should a program or an overall system run is kind of the number of processors, right? If everything is just kept busy, then it utilizes all the processors rather than having lots of processors and have the operating systems deal with that. Now, I do realize that there is a little bit of an oddball in there. In the past, we basically had the operating system do all the asynchronous stuff, and we basically just did blocking work, or this is also quite common. Now this stuff gets more into the user level land, which I think is basically driven by wanting to make it more efficient, more faster, reducing the overall overhead of everything. So you could argue, well, why not have the operating system do things and I still just do synchronous blocking work for most of the things, but it seems it's more efficient and faster and possibly also easier to deal with if you actually get that into the application. Okay, so as I mentioned, asynchronous interactions are around since a long time. There's nothing really new about that. So let's talk briefly about or a little bit about the basics. Because I forgot, if you have any questions in the meantime or comments, please raise them at the time. It's fine. Well, I can cope with that. So the basics of asynchronous work, from my point of view, is kind of I have a very different view than going from a very theoretical view, go more from a practical view. How does it actually work? And to me, there's basically a few steps, a few parts which are kind of common. The first one is you represent the actual work. Now, obviously, in programs, we represent work already, but typically implicitly in the form of function calls. You get work done by calling a function. In an asynchronous world, it's often way way more beneficial to say, all right, I actually do not represent the work by an actual call, but rather I reify an entity and I have an entity in my hand which represents the work I want to get done. And we can use part of the reason this is nice is once we have something represented as an object, we can actually take this object and give it to something which sends that work over to a different place. For example, it sends it to a GPU or it sends it to a different thread, or we compose the work into multiple things. So, and this is quite common in pretty much all the things which are in the space to say we represent actual work as an entity. Once you have an entity which is not yet running, because it's represented as an entity, you eventually start the work. Once you have started the work, the thread basically who started it goes kind of, I have nothing to do at all with that work. This is no job for something else with whatever we started it. And I will talk a little bit about how this actually looked like. And while the work is started but not completed, the current thread of execution can do whatever else it wants. The only thing which is important at some points, things need to get back to, okay, something completed and we need to carry on. But this is an entirely separate story, right? We start work, eventually things get computed and completed. And the completion probably gets somehow the result of the work. And because I'm in the networking area, I will have a very simple example. If you hope for cat images, I'm not good at creating cat images because I don't have a cat, so I cannot shoot one, and I'm not good at finding cat images, which are free and all of that, so I don't have images. But clearly, most of the work we want to do on the internet is we want to serve cat images. And if it's not cat images, it's cat movies. That's just pretty much the same thing. And yes, I know, dog images, same thing, right? It's kind of fine. I go with cat images, I prefer cats. So this is an entirely synchronous sequential implementation of getting a cat image, right? We have a client, we somehow receive a request from the client to say, give me this particular image, or give me that resource, or do this computation, right? It's not just cat images, it's all kind of other things, whatever you want. Then we basically obtain the resource which is requested. In this case, we read a file from a name and we somehow get that result, and then we send that result back to the client. Now, this is all sequential, and we have the opportunity to go and say, while we receive the request, while the client has not sent the complete thing, we can do something else. And then once we have that, while we acquire the file, we can do something else. And then once we have that, while we are in the process of sending the response, the thread can do something else as well. So a number of opportunities. So the way I visualize that for now is going, say, something like receiving a request is basically, once we started it, we basically tell some kind of magic black box to say, I want to get the request from the client. And we basically, or before we started, we have something, the client references a black box, which will help us to get it. Once we started, we basically say, right, we have some kind of or receive operation, which has some connection information where we get things from and a way to complete. This is, I talked earlier about we need to have a start and a complete, and we basically just can represent this is how we complete as well. And then once we started it, we basically tell the black box we know about to say, oh, let us know once we are completed. And we entirely offload all the work to the black box. And the black box does whatever it does. We don't care. And eventually, the black box says, yes, you're completed. We complete. The black box forgets about our entity. And now we carry on with our next step using the cat. And all the magic happens in the black box. So in our example, we basically could go the receive request. Here we have it. We can basically split that up into we ask something and we complete something and we do something in between. And conceptually, this is not how the standard does it in the end, but conceptually it does it like that. We have a receive request, which tells us about a client, and we have a completion. And the important part is that the completion is not an immediate execution, but we actually also represent how we complete. It's kind of, in this case, just a function object. The standard interface doesn't use a function object, but a receiver, which is effectively a generalization of a function object. But this is all there is to it. And then all we need to do to get the function, the next step, which is currently still sequential, well, we apply the same idea, right? We read the file, we get that sequential, and carry on. And then same with the response. And now the response over here currently has an empty placeholder. We complete with something, but probably we don't really want to drop that on the floor. We actually can pass in a completion, and then we kind of close the cycle and basically have something. When you start something, it always completes. And this relationship is very important for actually managing entities, because once you have something which is started and you know when it completes, you know you only need to have resources for the completion, where it completes, alive for the time between start and completion. And then, so you may be able to hold that in a local context, so you don't need to allocate it on the heap or something, and get rid of it. Okay, so this is basically turning something from kind of sequential and blocking synchronous into an asynchronous approach. And I already talked a little bit about representing work as objects. So part of that is work can be created lazy, which is saying, right, it doesn't do anything, we have work. And then you can compose more into it. We can use multiple of these lazy outstanding work. And once we have composed all of that, we go now start the whole thing, and it will just unravel, starting on the innermost things to kick them off, and start that to basically get our real work. And then the work is completing again within work, with an object. And one nice thing about composing work is this is what I believe most people will actually use once we have stood execution, is something like the composed work or composing work can be done with a coroutine, which is actually fairly easy to write. Once you have a coroutine implementation. The coroutine implementation is not hard to write either, but this makes it really easy. And I will have a little bit of an example for that. Well, actually, here's an immediate example. We could write the same thing we did before by basically, instead of saying receive request and getting a completion, one could have an interface which has receive request, which returns something which is available. We co-await that and we get the name out. And while this is not real code, some code like that could be made to work entirely. And the entire difference basically is we took a handful of co-awaits and put them over the code into strategic places. And the other important difference is you actually do not get a result out, but you rather get a task out. And the task is basically just another piece of asynchronous work which somehow needs to get started. But I will get to that, how that looks like. But this is actually the transformation from sequential code to entirely asynchronous code is not necessarily super complex. If everything is done right, all you need to do is put in a couple of co-awaits and turn something into a coroutine. Okay, now I talked about the black box where we do all the magic. Now let's look at how the black box could look like. And I will start off with the less usual, but actually easier approach. And that is if the black box is implemented in terms of operating system level completion operations. This happens, for example, for IO ring, where you basically schedule work onto the entity, and the system informs you effectively via some kind of a queue where complete work emerges. That work is now complete. Same is true for way longer than IO ring for IO completion ports on Windows. IO ring is Linux only, and IOCP is Windows only. Although when I say IO ring is Linux only, there's actually kind of an IO ring clone for Windows as well, which works very similar as far as I know. And the idea over there is all we do is when we start our operation, we basically say something like we have an add with some kind of opcode and parameters. That's just an object saying this is where this is the parameters for the operation. This could be something like for IOU ring would say, all right, I want to read, and here's a buffer to read into, and the other important part, which is supported over there, is to say this is where we complete. On IOU ring, it's not really saying you can complete, but you can pass in a pointer which comes back, and this can be a pointer to function. So effectively, you can tell the system, call me once you're complete, and all we need to do once we are complete is we call that completion function, which is pretty much what something like a run function is. So the layout of an asynchronous program using that would be you start off work, and this initially adds some kind of work into the black box, and then you call run, which runs that over here infinite loop or until nothing is there, whatever, however you formulate that. And this is obviously a little bit made up because the auto-res does not compare to bool. But conceptually, this is the idea. We basically run as long as we can get things, and all we do is every time we get a response back, we just complete that. So this is not quite the code, but it's not much more complicated. So the black box is not something really complicated either. And likewise, there's the more conventional approach, which works pretty much the same, except that things are a little bit more complicated to set up. And this is the more typical readiness model. This is what something like POL or ePOL or KQ interfaces do, where you basically say, all right, I have a list of work items, which is realistically just kind of a list of file descriptors together with an indication of I want to be called when something is readable, or I want to be called when something is writable. And all we do over there is when we have work, we basically add something to that list, inform the operating system in our call to POL or ePOL or whatever it is, to say, tell me if anything is ready. And then they differ a little bit how you get back the idea of what is complete. POL gives you an array of all the things, and the difference between things like POL and ePOL is primarily making the communication more efficient to say, right, these are the new things, give me back only the things which actually are completed. This is more like KQ and ePOL do, whereas POL always goes, oh, here's the entire list, and you get back everything which is ready at that point in time. So from a structure point of view, even if you do not have IOU ring or IOCP, implementing the black box to do I/O is still fairly simple. There's nothing magical in there. We can all do that. And this is, and all of these things can be reasonably cheap. Like, okay, if you have a huge list of file descriptors you need to add to POL, that becomes somewhat inefficient. This is why we have KQ and ePOL. But conceptually, this can be done, and if it becomes inefficient because you have too many objects, maybe you need to run multiple threads. But just because you want to do a bunch of requests and responses at the same time, probably you're just fine even with a really simple implementation. Okay, so now one thing which is important in all of that is the interesting idea of cancellation. Because once you have things where you do not just start running and you just complete as in a function, but you actually start something and then you go off and do other things, it may become really important to cancel things. And when I say canceling things, that is actually not an uncommon operation. It's actually quite common to say, all right, I want to wait for input for a certain amount of time. And I either time out or I complete. Either way, I have one operation which is outstanding, and I want to cancel that. After timeout, I want to complete the read. After completing the read, I want to cancel timeout. So this is actually super common. It's not something, oh, cancellation never happens. So building cancellation into the system right from the start makes it actually really, really nice and powerful. And I don't know whether people have created multi-threaded servers or systems which ask for things, and you brought them up, and then they run, and you get rid of all the race conditions, it's a masterpiece if you then can shut it down. Right? Because cancellation is typically an entire afterthought. But effectively, shutdown of a concurrent system amounts to, well, we brought it up, and now we cancel all outstanding work. And once everything is actually completed outstanding, I can cleanly shut it down. And I found this even relatively simple creation of sender-receiver-based stuff, because cancellation is built in. Bringing up something and shutting it down is always clean, because you always have the, but I will get to that a little bit later, you always have the property, anything which is started also gets completed. And to get things completed may amount to, all right, you need to cancel it. And hopefully you can cancel it. And if you cannot cancel it, then something sits out there which you have to wait for, possibly indefinitely. But all IO-like things or timers can all be canceled in the end. So this is actually an important aspect. And all right, I mentioned already the example, kind of wait for input. This may take too long. We eventually, like if you have a server and you, or for cat images, right, and you have some client who goes kind of, all right, I know what I do. I will basically be hostile and I will create 1,000 connections, and I will basically allocate all the connections and nobody else come in. If they then just sit there, it becomes really free for them to have a denial of service attack, right? You can run out of file descriptors eventually. But if you have at least a timer to say, right, if you do not give me a request within a certain amount of time, I will actually terminate the connection, that is not as easy anymore. So typically you want to have timeouts on certainly external connections, but you may also want to have timeouts on something which you actually control, because often if things take too long, you may want to write a warning and say, there's something going on over here. You need to investigate that. Okay. So, and then the other part, which I already mentioned a little bit as well, and which is actually really key to me, is kind of a coroutine interface is to asynchronous work is really, in my mind, where it kind of is at. The problem with the coroutine interface is, unfortunately, you cannot as easily or as efficiently build all the algorithms you may want to build. I will get a little bit back to that. But the basic idea in C++ to get a coroutine interface is, well, asynchronous work in C++, on with the coroutine is represented with an awaiter or awaitable. Like the difference between awaiter and awaitable is just an awaitable needs to have a co-await operator, which turns the entity you have into an awaiter, and then the coroutine will await an awaiter. Where an awaiter is basically something which has 3 operations. This is first something which is called await ready, which is primarily there for an optimization, which says, all right, is there something which I actually need to suspend for, or is the result already present? This sounds a little bit unusual. Why do I need that? But if you think of, let's say you read something from the internet or from the network, you may have got a buffer filled of data and you only use the first part. And next time you call the same interface, it will go kind of, right, yeah, I have already things in my buffer. You can try to use that. So you may have a readiness interface so you don't suspend. The next part over there is really the start operation I mentioned, which is called over here await suspend. What this does is it basically sets up the asynchronous operation to go off and do whatever it needs to do, giving it a handle to the coroutine. The handle is what is used to basically resume work eventually. And then the third part is often you want to get the result back. And this is basically to get the result back, you resume something. You resume the coroutine, where the coroutine is resumed by basically calling resume on the handle. This is once the asynchronous operation is ready. And then await result is the function which the system calls to basically produce a result for co-await. This is the result type. And then awaiters, okay. The awaiters basically require that you have a coroutine which understands co-awaiting them. But this is relatively straightforward. Okay, now this is kind of the background why and how we want to do that. Now, I want to talk on a very high level rather than going into very deep detail about the standard interface. And this is basically the standard's idea of how we represent work is a sender. A sender is effectively nothing else than here's all the work we want to do. It can be a really simple, basic request, which may go from actually produce just this value, actually once get started, which would be synchronous. This is basically the just operation, but it can be a huge graph of work which reads lots of things and does responses. So let's say it does an entire HTTP request response channel, or does deal with a client connection. All of these can be senders. They basically, more complicated senders are basically just built up typically out of simpler senders using some kind of algorithm. And one part which is important in here is senders are lazy. Once you basically created one of these things, nothing is happening yet. And if you have a sender and you drop it on the floor, that's fine. It will release all the resources, and it just doesn't do any work. The only interesting thing which happens is once you have started it, then it becomes, well, once you have started it, there's a contract which has to be obeyed, and I will get to that in a little bit. But the important part of these things being lazy is work can be composed, and then the work itself becomes a sender. So let's say here's a very simple composition of an algorithm, which is going kind of right. I want to basically read my request based on a more simple read buffer operation. And the entire idea is over here. I have somehow a client which may buffer things, so it extracts something. And I need to deal with buffering because on something like a TCP connection, you never know how much data you get, and there's no built into TCP, there's no framing, so that you only get one buffer. In practice, normally, if a request comes, you typically get it as one buffer, unless it's too big for the buffer. And you don't get multiple requests in the same thing. But if things are a little bit slower or things get combined on the way, you don't necessarily get that on boundaries. So you need a buffer. You extract something from there, and then the real things over here is we co-wait for read buffer. And then we may want to go and say, right, if we didn't read anything, then we bail out maybe with an error. We can bail out differently, completing the thing independently. Over here, because I return a string, if I'm successful, I just bail out with a buffer for simplicity. But this is an entirely simple composed sender. And this is, in fact, how I imagine most of the time users will actually deal with composition. They basically create a coroutine which does more things. And the C read buffer thing can itself actually be a coroutine itself as well. Now, if you went to Lucian's presentation, he talked about something like let value. Let value is kind of inside over here as well, as in we basically hold on to the result of the previous thing, and we can do more work, and we create a new sender, and we execute these things. It's not quite as structured as let value is, but it's easier to write on and more familiar. Okay, so the one thing which is interesting and which most of the preceding systems didn't have is the completion and sender receiver actually is not just a function call, but it's actually a receiver. It's an object which has more structure. And it has 4 important parts to that. Any one of them can be missing, or actually, in principle, a receiver needs to have at least one of the set value, set error, or set stopped. It may not have any others. It can, for example, only have a set stopped in case, which means your the work, the only way this receiver can receive results is if work gets cancelled. But that is valid. but you can have all four, and it's actually quite common for generic algorithms to have all four. The first one is the success case. So, right, this is what happens. We get values from whatever we did. The second one is set error, something failed. And the third completion is we get cancelled. Now, distinguishing between these three and actually having them different functions and operations is quite nice, or is not just quite nice, but it's actually quite important if you want to create higher level algorithms. Because you probably want to do something different when you have something like an, let's say, a when all operation, which has multiple senders outstanding. If one of them fails, you know your when all completely will not be successful. On the other hand, when it is completed successful with something like set value, you just want to wait for all the others. Whereas in an error case, or if one of these operations get cancelled, you probably want to cancel all the others, and you basically forward the error or set stopped operation. However, to actually correctly do that, you need to recognize what kind of completion you got. And this is way easier if you actually distinguish between these calls instead of having a result coming into a function, into one function, which you had to then, each algorithm would have to decode to say, oh, was that an error, a success, or a cancellation? And then there's another actually surprisingly important aspect to receivers, and that is what's called getEnv. Now, getEnv is actually nothing which is really related to receiving the result, but it actually channels information in the opposite direction. And that is getEnv allows the user of a sender to inject information about how do we want to, well, what kind of environment we want to have. And typical things which are inside this environment are things like a stop token, which tells us how do I cancel that thing. Or there could be maybe a database connection. This is how I want to connect to a database in there. This is not a standard thing, but you can extend things to basically say, all right, I want to get a database connection, or whatever context you need. Now, one interesting aspect of this entire asynchronous stuff is that you cannot rely on any global or thread local state. You basically, because everything happens at the same time, and the problem with asynchronous work is it's not just running on one thread. It may run a bit on one thread, get suspended, run on a different thread. This is where it resumes. Even if they come from the same scheduler, which is kind of the entity which says, right here, we want to run things, it may be a thread pool, and initially you started on one thread and you resume on a different thread. So thread locals is actually not a way to channel any information for any context. And there are many contexts which are relevant, right? Like a database connection, or let's say an access token, or a logging mechanism. All of these things come from somewhere. Yes?
Would you say it's fair to say that this environment is kind of equivalent to, like in C-style callbacks, the context pointer you get, so you can like write data out from a callback that another library is giving you, for example?
Well, the context is not equivalent to a callback. It's kind of more equivalent to a basket of things, which you can query to give me whatever you believe is in there.
Right, okay. So like if you've got a callback where you're reading from a file, I can use that to put data back into my own structures, say, for instance.
Yes.
Okay, cool.
Yes.
Hi. I got a bit confused when you were talking about the black box, which is generating our cat images, and you were talking about the very important thing of cancellation, which is great. From looking at this API, it looks like externally I can say, I'm giving up on this request I've submitted to the black box.
Yeah.
And are there any stipulations on that? I can call it any time and the right thing will happen?
Well, okay.
You can say no.
So assuming the black box is correctly implemented, yes,
Yeah,
you can
yeah.
cancel at any point in time. Now, the interesting aspect of cancellation is always if you cancel something, it can actually, at the same time where you cancel, it can complete. Right? It can cancel on one thread and complete on a different thread if you have more than one thread in operation. which is a little bit of a problem, but basically cancellation is kind of always considered to be racy. So you need to basically have the necessary thread synchronization
Sure.
in
That's
there.
given.
But if everything is correctly implemented, yes.
Yeah.
Like the I/O context should allow you to go and say, I don't care about this operation anymore. Even if the operating system doesn't know how to do that, you could basically effectively null out the pointer. And when the operating system says, oh, I'm ready, you go kind of, yeah, well, but that is gone.
Got it. Yeah.
Right, so-
And kind of related, I think you touched on this, is like when the black box itself internally decides to give up on a request, so we don't have a response. So it becomes stopped. Is it all the same interface as far as the client's concerned?
So whether a black box on giving up actually sends a cancellation is not clear. Probably more likely sends an error
Right.
and says, this is the error why I did not satisfy that result. But in principle, it could send a cancellation. This is kind of any of the async operations. You can choose how you complete. So you can absolutely have an async operation which deliberately cancels things from there on and says this is what it is. In practice, it's more useful to cancel once you actually are asked to cancel and rather produce errors otherwise. But technically, it works. Okay? All right. So the receiver mostly getting results, but also it's a way to basically inject customization from the use side. Right? You build up all the work graph, and once you have all the work graph, customizations are injected kind of from the starting end, which I think is actually an interesting approach. And it's actually, in my mind, very, very powerful. Okay. Now, I talked a little bit about the inert work, which is basically sender, the receiver where results come, and then there's another player in the game, which is effectively an operation state. An operation, or it's what's called an operation state. An operation state is basically work which is ready to run. So what was meant over here, it does not just know what to do, but it also knows where to deliver the result and how that is done. So basically, it's a result of connecting a sender with a receiver. And so that's where these things come together. And the state is still just sitting there and doesn't do anything. So you can start it eventually, or you can drop it on the floor. Starting, basically, you just say start state. And then it starts. And this is where a binding contract comes in, which I hope is on the next slide. No, it's not. Okay, so one part over here is, for example, if you want to cancel things and you basically, or you want to support cancellation, the cancellation comes typically from the consumer side of the sender, not from the build-up side from the sender. So basically, the receiver provides access to a stop token. There's a function get stop token, and the stop token is basically an entity which supports essentially two operations. There are a few more to make things more efficient, but it supports one. You can ask an operation which is ask the stop token whether stop was requested. So stop token is somehow connected to something which can produce stop requested. And so which is typically called a stop source. So somebody's holding a stop source, like if I want to bring down my server, I have a stop source on the outer side, and maybe I have a request I can send, which will set on the stop source, request stopped. And then after that, any stop token obtained from there will say stop requested, yes. And then the other bit is, because stop requested is only useful if you once in a while can poll things, but if you actually have inactive work, this is basically something where you send, for example, ask the operating system to wait for a read. There's no active work. The thread never gets control until it is completed or errored over there. To basically deal with these guys, you can also register a callback into a stop token so that you have a way to basically call out to the black box, for example, and say, oh, cancel that, please. So this is, both of these things are important. The stop requested, there was already a stop token in C++, I think 23, which is extended to also have a callback, which didn't exist before, to basically call, get invoked when stop is requested. There is interesting racy conditions in that space, in the sense of when you basically call stop requested and have all the callbacks called, you need to be very careful to make sure that the stop token or stop source doesn't accidentally get destroyed before you're done doing things. But hopefully the implementation of corresponding algorithms is correct. Okay, now I want to actually talk a little bit about the key sender-receiver contract. And the basic idea is, if you have an operation and it completes, you know that all sub-operations this particular operation started have completed. The reason you want that is this allows you to basically embed any completion state into the outer operation, which starts any sub-operations. You don't need to allocate any memory somewhere on the heap to basically deal with that or have things uncontrolled. That's basically a structured concurrency approach to say, right, we start things, we start possibly other things, but everything we started has to complete it before we complete ourselves. So this is one part. And then the other part to actually make that happen is, once an operation state is started, it will result into in exactly one completion function on a receiver. And the receiver may be the original one, it may be a copy or moved version of the receiver. So there's a little bit of a leeway to move the receivers around, but once started, there's one call. The other part, which is actually important for the implementation, is operational states can be movable, but they're not required to be movable. And any implementation using an operational state should assume it's not movable. This indeed gives another very powerful approach, and that is you actually have an object which you know, right, this stays put. I can set up internal pointers into this object as much as I want because this stays there, which again helps with not having to allocate any extra memory for any of the state. Okay, so yeah, I think I talked about most of these things. Representation of work, starting the work, this is what it does. One thing which is sometimes important, work may complete immediately if there is nothing to wait for. So start state may actually call the completion function on the receiver before start state returns. This is a typical case, for example, if the state came from a connect of just and the receiver, all just does is it produces a value. That value is ready. It will never wait for it. So start return the completion functions are called before start returns. In actual asynchronous work, obviously start will return way before the receive operation is the receive operations are called. And then once started, set value, set error, set stopped are called. That is a promise. Now, one thing which this guarantee does not really make is how long it may take until one of these operations is actually called. And obviously, if a program crashes or something like that, that guarantee is out of the window. But in normal operation and non-fatal operations, one of these operations should be called, even if you turn things down because you cancel it. Okay, now this is kind of on the very high level about these things. Why is that interesting? If I talk about all these, when I talk and say the composition mostly will be done just using a coroutine. You basically just create a task and you basically compose things by doing work inside. There are some interesting algorithms which can be implemented with a coroutine interface, but doing so is actually way well, I don't know how much more inefficient it is, but it's probably more inefficient and definitely will need some memory allocations. And example algorithms of that is something like when all, where when all is a nice opportunity, which actually makes it simple to do multiple things at the same time and carry on when everybody is ready. So when all with multiple senders does is it creates a sender, which when started, produces the results of all the senders. It basically returns a tuple of all the results. And the other operation it does, well, if it's successful, but if one of the children fails, it basically, and failure meaning set error or set stop is called, it cancels all of the outstanding work. And this is actually really nice to say, right, I want to have these multiple long-running things concurrently done. You just call when all and it just happens. And the other, this is one of standard algorithms, or which is proposed in a standard. The next one, when any, is one which I always want, because I want to deal with things like a timeout, and when any is naturally written as something like resume after some time, or do work. When we basically complete once one of these is completed, the other one gets cancelled. Once that completes, probably with the cancellation, we produce a result of the first. And this is the basically when any algorithm. It's not super hard to implement, but implementing that in terms of an coroutine interface is actually not as easy. And you actually need to actually implement a coroutine. It's as in the coroutine interface. You cannot implement that by basically using, let's say, a task. Because every co-await, if you co-await one sender, it will await that sender, and then the next co-await awaits the next sender. But these things happen sequentially. Whereas over here, you want to start things concurrently and finish when one of them happens. Okay, so to get all of the things finally to work, we have all these algorithms, we have the senders. There's one important data structure which is built on top of that, and this is basically what is called counting scope or scope, which basically has the idea we have a sender which is currently not doing anything, and we somehow get the sender interface says we get a token, and we bring the token and the sender together with what's called a spawn operation. Now, spawn doesn't create any threads or anything like that. All it does is it probably allocates a little bit of memory, which is registered with the scope to basically hold on to that. It basically connects a receiver to the sender, and all it does in that receiver is whenever any of the completions come in, it basically deallocates the memory and decrements the counter. So this is where the counting scope name comes from. It basically knows how many outstanding work do I have in there, and once it gets to zero work, it can call and, all right, I'm ready, completion on a sender, which is basically something like an, I don't know, it's called, I think it's called something like on empty or something like that, which is a sender which triggers once the scope itself is finished or has nothing in there. Okay, so the question is the completion on empty thread called on the same thread as the one which completed the sender?
Yes.
And and the answer is probably. I don't think that is generally a problem, because this is actually just a completion signaling that something is complete, and you can actually schedule wherever you want to run any follow-up work on this being empty to go wherever it is. Most likely, this is basically just telling something it's done, which is running in a sync wait on the outer level, and that sync wait will then go kind of, right, yeah, this is done, and I can bail out of my loop because there's no more work.
Yeah, so I'm thinking in the context of a desktop app where you've had something to run, and then you basically want to reflect that in the interface. So
yes,
when an event comes in, you processing events, you could basically check that scope and you could see that it was completed and then do what you needed to do.
Yeah. There's a few slides on. This is how I imagine a desktop app basically looks like structurally. Right? It basically has a sync wait for when all, which is basically a context run and a scope join. Context run is basically doing my I/O and what knows business, and scope join is waiting for the scope to get empty.
Right, okay.
Right,
Thank
and
you.
basically
Yeah.
when the scope is empty, hopefully there's no more work outstanding. So the context can complete because it does not have any more work and be complete. This actually works quite nicely. What is missing in here, obviously, is you can give or I didn't show that the scope has basically a join operation. This is what I mentioned over there. So a join operation, which basically all it does is join is. I claim something different over here, but on the slide. But basically, there's an operation which says finish the scope, don't accept new work, which basically cancels all work in the scope. So in a desktop app, you probably have some way to shut down. This will then result in the I'm all empty, and everything nicely shuts down.
Great. Okay. Thank you very much.
Right. Okay. Cool. And I see you. Lucian in the front row, quickly looking things up. I hope he doesn't want to correct me. No, you. Yes. Oh. Okay. Yes. I didn't get the names right, probably. So don't name me on the names, but conceptually what I'm talking about is definitely true. Yes.
How does the scope token relate to like the cancel token? Are those the same thing, or
it's not entirely? They are entirely different things. The idea is that they have some relationship conceptually, and that is you somewhere have a stop source, which is something which stays put and you cannot copy. And to refer to that, you pass around stop tokens, which basically are lightweight. Essentially, they're just a pointer to stop source. Similar for the counting scope. You have a counting scope, and you can pass around scope tokens. You cannot pass around the scope. That stays put wherever it is, but the tokens are easily copyable, and you can pass that wherever you need to. So there's kind of somewhat it's a little bit more than just a pointer, because to basically, it also kind of reference counts the outstanding tokens, so that you don't have the problem that you have a token which is pointing to cell memory because you finished ahead of time. So this is what the background over there is, and you don't really want to pass just pointers through because they kind of control that. Okay, but yeah, as I just described a moment earlier, is kind of the typical asynchronous work, how I imagine it would be normally used is you set up an I/O context or a thread pool, depending on whether you do I/O or computations. You may have both, because you do both a networking interface as well as computations. Once you have set that up, you then create initial work, set up accounting. And probably this is if you have dynamically created work, otherwise you don't need a counting scope. If you know all your work, you can probably deal with something like a manual. But if you have some kind of dynamic work being created, and what I mean over here is dynamic work would be things like a client connection coming in, or an algorithm which basically does things in parallel, spawns off multiple things concurrently. This would be dynamic work. If you have any kind of dynamic work, you probably have a counting scope. You put the initial work, set up the initial work, kick that off, and then you just wait until things happen. And this is basically the outline for the I/O case, which does just that. And I think this is relatively comprehensible and easy to do. And then the only question is, what kind of work can I create? Unfortunately, the standard library will not provide any concurrent work in any shape or form. It has a nice infrastructure for doing all of these things, and you can create something like an I/O context, but there will be no I/O context. There may be a a thread pool, but the thread pool itself is actually also not providing asynchronous work. You have a place where you can do asynchronous work, but asynchronous work is basically something which needs to be created. Now, some people may remember that we have async in, or I think it's called async, right? In our standard library, which basically is something like we're creating a thread and a future and all of that. And this was not a big success because people expected we create that, and then the next revision of the standard will provide things we can actually do with that. That never happened because people went kind of, yeah, we don't want that. And it was very hard to actually use async, and async didn't make any useful promises either. All it said is kind of, all right, yeah, we complete somehow. And if you actually did that, if you called async, typically what would happen, there's a thread being spawned, and this is what nobody wants. Right? You don't want every time you have asynchronous work, a thread being spawned. Will that happen for sender-receiver as well? I doubt, for two reasons. One is you actually can create your asynchronous work. Anybody can, in principle, create an I/O context. It's not something you can do necessarily in an afternoon. But if you want something like that and you want a library which does I/O things, it's definitely doable. Maybe it takes a week of work if you know what you need to do. If you need to have a thread pool and you want to have asynchronous operations, asynchronous algorithms, it can be done. It's not shipping with the standard, most likely. There's still some things in flight which may get in, but probably won't. I expect a whole bunch of things coming with the next revision of C++29. Until then, people will probably have to make do with things they get from NVIDIA, they implement themselves, they get from some projects like Beeman project or something. Okay, what else do I have? Okay, so yeah, earlier I showed how to create the cat client, cat server client thing. This is basically the initial work, right? If you want to go over here, basically use the run server. This is how the run server would look like conceptually. There's probably a bunch of details which are different, but it's entirely doable. Again, you basically just have create a server. In my for loop, because I'm kind of somewhat live over here, right? Every time I whiz around, every time I get a new exception, a new connection accepted, I could check a token. There's already an algorithm in the standard library called readenv, which basically looks at the environment, in which case over here, since it's on a coroutine, the coroutine would need to provide a receiver with an environment pointing to the stop token, but we can get that out, get the stop token, check it. If we are not requested to stop, we try to accept more work, and then if we have more work, we spawn that into the token. So it's actually relatively straightforward to create work. It's relatively straightforward to cancel things and all of these things. So I'm actually very excited about that. So I probably finished a little bit early, but anything in my mind which could block should be asynchronous. And a lot of the things we currently have are not in that space, which means there's a lot of functions which probably do I/O under the hood, and all of these should actually be asynchronous. This will not happen overnight, obviously, but hopefully that happens over time, so that we basically get all asynchronous stuff. Hopefully not hopefully, I think the standard interface allows different libraries to play together. This is one reason why it needs to be standardized in my mind, to say, this is the interface we all want. It is generic enough that it does work. Existing libraries can actually be adapted. Let's say you have an existing async interface. It can be done to say, all right, I basically create a sender which represents that work, and create an operation state internally. Once I started that, I call whatever the underlying library does. And using all of that via a task, which unfortunately may not make C++26, should be reasonably straightforward. And with that, I just say, all right, these are the other presentations. I basically gave the first in the first presentation. I should have given the presentation today before all the others to give more context on how that works. The structured networking stuff basically gives you an idea how you would create the black box. In case you don't get the task, the co-wait all the things basically shows you how to create a simple task. A real task is a little bit more work, but I had only an hour. And then the top one over here is basically creating a simple HTTP server live. You can see how to code that, and I get it to a stage where it actually does work within an hour. All right, thank you very much.